So now in this smaller session, I would like to discuss another method for generating random number sequences of other distributions. So we are still in the section of random number generation, and we are discussing how we can generate drawings of other distributions. The most popular method is indeed the inversion of the distribution function, but you already saw that this relies that you have a formula for the inverse of the distribution function, or you have maybe a good approximation. And sometimes you do not have this, but you have other things. So a nice example is the normal distribution, and it will pop up later, because for the normal distribution, we know the density. The density is very nice, yeah? 1 divided by square root of 2p exponential minus x squared half. The density is very nice, but the distribution function is not known. Okay, we already saw that we have accurate approximations, so maybe it's a little bit an academic example, but it is a nice example where you know the density, but you do not know the distribution function. A method that can be used in this case is acceptance-rejection sampling. And although I believe that the method is, well, not used very often, because quite often you can find an inverse or an approximate inverse of the distribution function, it's very nice to study the method, also because it will later motivate the method of weighted Monte Carlo, because weighted Monte Carlo is a little bit like doing acceptance-rejection sampling. Okay, so what's the situation? The situation is, again, that I would like to generate an F-distributed random variable. Let's call it X. Okay, that's our goal. The problem is I do not know F inverse. But I know the density of F. So I know the density F prime. And there's one other condition. We know how to generate another sequence, a G distributed sequence. This is the sequence yi. So this is a G distributed sequence. Where the density of G fulfills a certain condition. So, and this condition is that there exists a constant C such that C times G prime is larger or equal F prime. So I need some other distribution function, and the density should dominate the other density. Okay, and that's a very hard condition because the integral of the densities have to be 1. Yeah, so I'm of course allowed to shift the density of G a little bit up. Yeah, so actually the constant C, yeah, we will see it has to be larger than 1. Yeah, if it's equal to 1, actually the two are the same. Okay, so and maybe I have this situation. And if I'm in this situation, then I can generate an F distributed sequence. And you see here that you only need the density of F. Normal distribution is an example. I have here the density of X. So maybe that would be an application. So here is how the method works. So it's called acceptance-rejection sampling. So let F denote a distribution function. It's the distribution function of the sequence I would like to generate. So that's actually my target here, the sequence xi. So given are now drawings uj and yj from random variables u and y. So u is just a uniform distributed random variable. So u has uniform distribution. Okay, we know how to generate that. Yeah, we have random number generators that generates uniform. And y is a G distributed random variable. So maybe I need to have a second generator that now allows me to generate this second component, and this second component should be a G distributed, a drawing of a G distributed random variable, y. So maybe later we see that this G could be just created by an inversion method applying G to the -1, the inverse of G, to some V, and V is again a uniform. Then you know that you only have to generate a vector of two uniforms. The first one stays the U and the other one becomes the Y by the inversion. That could be a solution. So it's not a very complicated situation. So now let little f denote the density of my x, so it's the derivative of the distribution function f, and let little g denote the density of the y, so it's the derivative of the distribution function capital G, and assume that I have the following condition. So there exists a constant c such that the density f of x is less or equal c times g of x. Okay, so if you like to have a small picture, the situation is like that. Okay, here's your x. So then we have the density of f. So that's maybe my target distribution. Okay, so maybe that looks like that. Okay, that's maybe a normal distribution. So the normal distribution goes with an e to the minus x squared, so it goes very quickly. Then assume that the density G, so the density G, would maybe decay not so fast. So maybe it looks like that. But since it is above, there, it has to be below at some other place. So maybe it looks like that here. So it's just a little bit flatter and has slower decay to the ends. So this here is maybe your G. So for example, the exponential distribution could be one, or the symmetric exponential distribution, exponential minus x, well, x absolute value, then it decays slower than exponential minus x squared. So this is your G and this is your F. Okay, but then I'm allowed here to use the constant C, to shift this G a little bit up, such that it always dominates the density F. So this guy here should be then your C times G. Okay, so maybe we can achieve this. Then the sequence Xi just defined by taking the y at certain points ki. Okay, so you have here certain points ki. This is an f distributed drawing. So this is a drawing of, a random variable x with distribution function f. So you see, I do not take all the y's here. I just take y at some selected index ki. And now I have to tell you what's the selection criteria. So the I starts here from 1, 2, and so on. So let's just to be formally correct, initialize the k0 to 0. So k0 doesn't appear here in this xi equals y of ki, but k0 is 0. So then the ki is defined as the minimum index that is larger than ki minus 1. So that is the first one, the ki minus 1, I equals 1, the k0 is 0. It's just the first index that is larger than 0. So it's just some index. Yeah. But then after that, for say k2, it's the index that is larger than k1. So it's just the next one. So this condition here is just that you look at the next index in line. Where, and now comes the condition, our sampling u, so uj, is less or equal f of yj divided by c times g of yj. So from this condition here, that f is less or equal c times g of x, I actually know that this ratio here, so these are densities, yeah? Densities are positive. So this ratio is larger or equal 0. The density of f could be 0. But this condition then implies that also this ratio is less or equal 1. So this condition implies that this ratio is between 0 and 1. So actually it's some number in the interval 0 and 1, and I just make now a drawing of my uniform. So this guy here is my uniform, and I just check if the u is below that level or above. If it's below, then this defines the index where I take the value y. If it's above, I continue and I go up. So you see that this is actually a criteria to accept the point y or reject the point y. So in other words, these indices k1, k2, and so on are the successive indices for which this test criteria here is fulfilled. The uj is less or equal f of yj c times g of yj. And so now you see why it's called acceptance rejection. Okay. So in other words, what the algorithm does is the following. The algorithm to generate samples of x via an acceptance rejection method, yeah, so we have a criteria here, is to sample pairs. Okay, there's a small typo here, that should be a y. To sample such pairs, u, little y, and then reject the y until the u is larger than f of y c times g of y. And then accept the point, so set the x to y, if this criteria is fulfilled. Maybe the until here is a bit strange, yeah? So maybe it should be as long as this criteria is fulfilled, so u is larger than that. Yeah? All those guys will reject it. And once we observe that it's the other way around, we just take this sample point. Yeah, if you would like to have a small picture, yeah, it looks like that. Okay, you have your sequence of u's. So you generate u1, u2, and so on. You have your sequence of y's. So it's that we generate a vector. So this here is the y1, y2, and so on. Okay, and then you just check the condition on these guys. So you just check, is U, so the UI, larger, or is it less or equal the F, this is the acceptance criteria, F of yi divided by C times G of yi. So is this the case? So maybe I move this here. So if this here is not the case, then you do not take the point. So maybe you check here again. It's also not the case, so I do not take the point. And maybe here, if you compare these two guys, they fulfill this criteria. So this criteria is now fulfilled. And it will generate the point X. So maybe you have some kind of, you could say you have some kind of filtering active here that filters some points. So this point here, these two samples do not fulfill the condition, and so I do not take the point. And this gives me my sequence little x. So these here are the UIs, these are the YIs, and these are the XKI. So a filtering. So now the claim is that this filtering criteria, so it's actually this criteria here, will lead to the fact that we have an F-distributed random variable. Already a small remark, you see that, we get out few numbers. We have to actually generate twice as many numbers, and then there is an additional filtering, so we get out few numbers. So I would like to get out many numbers. So how do I get many numbers? So I get many numbers if this guy here is very close to 1. Because then I'm drawing a uniform, and it will very often be below, less or equal, the number that is very close to 1. If it's equal to 1, then maybe the two densities are the same. Then I'm just taking every point. Already a nice interpretation. If it's equal to 1, you are just taking every point. So this also means that you would like to make C not too large, because if you make the C too large, this domination, you are actually throwing away a lot of points. So let's prove this method. So let's prove that this filtering leads to an F-distributed random variable, and the proof will also provide you with more intuition what's going on. So first note that the probability that U is less or equal F of Y C times G of Y is 1 divided by C. So you see, this here is your acceptance criteria. So this means that this stuff here is actually the probability that you accept the point. So you see the number C, if the number C becomes large, the probability that you accept the point is small. Note that I'm writing this here in terms of random variables. So this is my uniform random variables. This is my G distributed random variable, my random variable Y. So this is a probability in the two-dimensional space here. This is the probability that I accept the point. And the claim is, or the first observation is that this is equal to 1 divided by C. Okay, so how do you see this? So if you have such a thing where you have a probability where two random variables occur, a nice thing is to just introduce a conditioning. So I will just condition this to Y equals little y, and look at the conditional probability of accepting the point under the condition that I know I have sampled little y. So then this conditional probability is, of course, just plug in that you already know the y, so plug this y here just in. Okay, so that's just the probability that the u is smaller or equal f of y divided by c times g of y. Yeah? So again, in this picture, this is your interval from 0 to 1. Then there is some bound, yeah, where you now calculate the f of y, c times g of y. And the question is, are you just lower or larger than this bound? Yeah, now you know u is uniform. So the distribution function of u on the interval 0 and 1 is just the identity. So you just get this bound, yeah, as the probability, yeah, of being below this bound. So now I would like to calculate here this probability of accepting the point. So the probability of accepting the point. And the trick is now that you do a conditioning. So you condition that y equals little y. Okay, then I have here the probability that u is now below f of y divided by c times g of y, under the condition that the capital Y is the little y. So this is just what we have calculated. So this is just this guy here. That's just the probability for a specific y. Yeah, so we have done a conditioning on a little y. And if I would like to have the probability for all possible y, I can just integrate. So integrate with respect to the density. The density is the little g of y dy. Okay, then you plug this in. So you have f of y divided by c times g of y multiplied with the density g. Yeah, then you see that actually the density is canceling here. You just integrate the density f multiplied with the 1 divided by c, integrating the density f over the whole domain is a 1. So this is just our claim, a 1 divided by c. Okay, that's already a nice interpretation. The probability to accept the point is 1 divided by c. Okay, so now we have to prove that x has distribution function f. So the distribution function of x is the probability that x is less or equal little x. Plug in now the definition of how we generate the random variable x. So the random variable x is generated by saying x is equal to y, but only if my acceptance criteria is fulfilled. So the probability that the x is less or equal little x is the probability that the y is less or equal x, because the y is equal to the x when I accept the point. So under the condition that u is less or equal f of y times divided by c times g of y. Okay, so that's here just the definition. That's just the definition of the x from the algorithm. That's just what we do. Next step, rewrite the conditional expectation, yeah, by saying, okay, it's the probability of the intersection of the set I'm looking at, y less or equal x, and the set that provides the condition. So y is less or equal x, and I'm accepting the point. Renormalized by all the cases I'm looking at. So renormalized by all the cases where I accept the point. So now I can plug in here my previous result, that I know that the probability on which I'm conditioning here, so the renormalization, the probability to accept the point, this is 1 divided by c. So I can plug this in. So this here is a 1 divided by c. So I know from the previous calculation that this guy here is the probability to accept the point. So this is equal to 1 divided by c. So I will get just divided by 1 divided by c, a c in front. And I have the probability that y is less or equal x intersected u is less or equal f of y divided by c times g of y. So now I'm doing again conditioning. Let's call here the y, let's call it a little z, yeah, and look at the probability that z is less or equal x, and the u is less or equal f of z divided by c times g of z. Okay, that's the probability that this event occurs, yeah, under the condition that y is equal to little z. And then I integrate this over all possible values, yeah, for z. So I multiply with the density. This is the density for y, so g of z dz. So what's the guy here inside? Yeah. So the guy here inside is the z where z is less or equal x. So, but I'm integrating over all possible values of z. Yeah? So that means I can just replace here this condition that z is less or equal x. I can just replace it by taking here in the integral the upper bound, yeah? And then I can just drop this intersection. Okay, then it's just the probability that my uniform is less or equal f of z divided by c times g of z. Okay, but u is again a uniform. We already had this. Okay, this is just the value of this bound. This is just the f of z c times g of z. Okay, so I can just write here again the f of z divided by c times g of z multiplied with the density g of z dz. Okay, and then you see that there is a lot of stuff canceling here. So the density g cancels. Okay, we had this before, like before, but also now the c here in front canceled, okay, because we renormalized with this probability. And you see I'm just integrating the density f from minus infinity to little x. That's just the distribution function f of x. So I started here on the left-hand side with the question, what is the distribution function of x? And I arrived at capital F. Yeah? It's the integral of the density little f. So you see, I only need the density. Okay, so that's a very nice method. Yeah, we just need the density and maybe some auxiliary sequence, yeah, that has some condition where the density of f also enters, but maybe that condition is quite mild. And the only thing, yeah, I would like to have is that I'm not too wasteful here with this condition. So I would like to find here some function c times g, yeah, that is, say, very close to the f, because if it is far away, so if this ratio c f divided by c times g is large, it means that this gap here is large. Okay, so if this gap is large, it means that I throw away points quite often. You can also look at this picture here and ask yourself what we are doing. Okay, so we are just sampling an X somewhere, and then we are drawing here this line and checking for the uniform. And is the uniform then above or below, yeah, this interval? Yeah, so where is this uniform actually in this area, or is it in that area? Okay, and by throwing away the right proportion, you are changing from the density G to the density F. That was it for today. Thanks.